By the end of this lesson, the students will be able to explain the terms Kp, partial pressure, and mole fraction, relate partial pressure with mole fraction, write the expression for equilibrium constant in terms of partial pressures, specify the unit for K, calculate Kp based on partial pressure. 0.5 mole of gas A and 1.25 mole of gas B are placed into two separate but identical containers. The pressure exerted on the containers by each of these two gases is 2.4 atmospheres and 6 atmospheres respectively. Click Next to view what happens when the two gases are mixed together. The two gases do not react chemically with each other. They each exert a pressure of their own on the walls of the container. Compare the pressures exerted by A and B before and after they have been mixed together. Discuss and click Next. Answer. The pressure of a gas in a mixture is the same as that exerted by the gas if it occupied the container alone. The total pressure is the sum of the pressures of A and B. This is in accordance with Dalton's law of partial pressures, which states that the total pressure of a mixture of gases is the sum of the pressures exerted by each of the gases present. The pressure contributed by each gas is called the partial pressure. Click on the button 1 to get the expression of the partial pressure of A according to the ideal gas equation. Now, click on the button 2 for the total pressure of A and B. Click on the button 3 to divide PA by PT. Click on the mole fraction button. The ratio of the number of moles of A to the total number of moles of all gases present is called the mole fraction of A. The value of the mole fraction is always between 0 and 1. Click the button 4 to obtain the expression for the partial pressure of A. Summary. Dalton's law of partial pressures states that the total pressure of a mixture of gases is the sum of their individual partial pressures. Pt is equal to P1 plus P2 plus P3 and so on. The partial pressure of a gas in a mixture is the pressure it would produce if it occupied the container alone. The mole fraction of A in a mixture of A and B is the number of moles of A divided by the total number of moles. Mole fraction of A is equal to number of moles of A upon number of moles of A plus number of moles of B. The partial pressure of each gas is equal to the product of the mole fraction of the gas and the total pressure of the mixture. Pa is equal to mole fraction of A times total pressure. The reaction between A and B is a homogeneous system as all the reactants and products are in the same phase. Click the Kc button to view the expression for the equilibrium constant for this reaction. When dealing with gases, it is more convenient to use pressures rather than concentrations. Click the Kp button to view the equilibrium constant expressed in terms of partial pressures. Partial pressures can be expressed in atmospheres or in pascals. Click the unit of Kp button to view the units of the equilibrium constant. The unit for Kp will depend on the unit used for partial pressure as well as the number of pressure terms in the expression. This is the equation for the formation of ammonia. Click the Kp button to view the expression for the equilibrium constant. Click the Substitute button to derive the unit of Kp. Phosphorus pentachloride decomposes to give phosphorus trichloride and chlorine. Drag and drop the appropriate partial pressures of PCl3, Cl2 and PCl5 into the empty boxes. Click the Calculate button to get the value of Kp. Summary: unit of Kp will be atmosphere or pascals if partial pressures are expressed in atmospheres or pascals respectively. The unit of Kp also depends on the number of partial pressure terms. Kp can be calculated from the values of equilibrium partial pressures. Dinitrogen tetroxide undergoes 60% dissociation to form nitrogen dioxide at a certain temperature. The total pressure observed is 1.5 atmospheres. To calculate Kp, click Next. Assume that there is 1 mole of N2O4 at the start. How many moles of NO2 are there initially? Click the button 1 to find out. How many moles of N2O4 will dissociate? Click the button to find out. How many moles of NO2 will be formed? Click the button 3. Calculate the number of moles of both the reactant and product present at equilibrium. Click the button 4 for the answer. Now, calculate the mole fractions of N2O4 and NO2 at equilibrium. Click the button 5 to check your answers. The total pressure is 1.5 atmospheres. What are the partial pressures of the two gases? Click the button 6 to check your answers. The partial pressures of the two gases can now be used to calculate the value of Kp. Drag and drop the appropriate values into the empty boxes in the expression for Kp. The value of Kp for the dissociation of N2O4 at this temperature is 3.4 atmospheres. The equilibrium constant remains the same as long as the temperature remains constant. Thus, we can use the value of Kp to calculate the number of moles of N2O4 that dissociates at different pressures, for example, at 2 atmospheres but at the same temperature. Click the button 1 for the initial number of moles of substances. Assume that X moles of N2O4 dissociated. How many moles of NO2 are formed? Click the button 3 to check your answer. Calculate the mole fractions and partial pressures of the gases. Click the button 4 and the button 5 to check your answers. To calculate the partial pressure, click the button 6. We can now use the value of Kp calculated earlier to work out the value of X. Click the Kp button to see how this is done. Summary: the following values of the gaseous reactants and products must be calculated in the sequence shown in order to determine the value of Kp. 1. The number of moles at equilibrium. 2. The mole fractions. And 3. The partial pressures. The value of Kp is constant at constant temperature.